Yeah. Take your cranberry wine off it.
Just keep going.
Dude, I think that there was some more. Every time I pop that lid, I don't know if that indicates it's still fermented.
I don't know.
They popped two off the big time one night.
Really?
Yeah.
Is that bad?
Increased pressure inside the bottles? What bottle?
I mean, it's
a
a
glass
mason
bottle?
jar, yeah.
Mason jar?
Yeah.
Uh,
I mean, it's still fermenting.
yeah, if it built up pressure. Well, it depends on temperatures. Because you could.
It's on the fridge.
Oh, yeah.
Yeah.
That was a bad one, yeah. That was a good one.
Yeah, no. Yeah, if pressure's building up, it's for something's happening. I was gonna say sometimes, you know, pressure and temperature are correlated. So if you increase temperatures, you increase pressure.
Yeah.
That's why, like, a lot of times you have to get cold, like really beer, so it doesn't foam up. It's cheap beers. It's cheap. It's in the mason jar. Was the lid bulging?
I didn't pay much attention to it. Like I would open the lid and like a loud snack on the top. Didn't like blow it out of my hand, but it
I wonder if the lid was bulging. You should check that.
and then gone out.
Yeah, I've had some that built up pressure. So I've only had one that exploded, and that wasn't even mine. It wasn't a mason jar. It was just a beer bottle. It was shortly after my youngest was born. Homebrew shop gave me a guy's peach wine, peach cider.
Oh.
Yeah, I didn't even get to have it. Smelled it. Didn't get to have it, but the glass bottle exploded at, I don't know, 3 in the morning, 4 in the morning, real early, and set off the glass break detectors. So you had the stupid alarm going off. What the hell? My mom was sleeping in the next room. I'm looking around at the windows. The big plate windows are still there. It's like I'm looking at the glass. Fine, walking around, and I see like a hint of brown, like shine. I look at it and I said, "What is that?" And then it just like clicked on me. Clicked on me. It was a bottle. Oh, you can again spend time on YouTube looking up exploding beer bottles, and you'll see horror stories of guys that like go into their closet and just completely explode. How many of you have seen Breaking Bad? So there is a scene where, yeah, the brother-in-law homebrews beer and the bottles were exploding. And he thought it was like people were like shooting his house. And that's what you got. And then, I don't know, I thought of it and said, oh my God, that's the beer bottles. Yeah, it can happen. It can happen. All right, so we got off. Side quest. All right, summary stats. I think we left off here, apparently, right? Right. You calculated all this for the temperature data within the water data set, right? And it all worked, right? Minimum, maximum, interquartile range. And I think we did that in the R Markdown package, or R Studio. Should open up for me. No problem. Basic stats. Yeah, here's all my summary stats. Close that down just a little bit. All right, minimum and maximum. All right, so those are the base packages, or those are the base summary stats. There are other stats that we use. And these are kind of important stats because anytime we report our data, we have to give that measure of central tendency and then some measure of dispersion. All right, preferred measure of dispersion when you are presenting means is actually standard error. Why is standard error preferred? Who can tell me?
Squared, same unit, is that right?
Okay, it's the same unit. Yep. So is standard deviation.
Function of the population.
Okay, it talks about something about the population. What is specific about it?
Like sample data, right? So you're comparing different statistical parameters, I guess. and
It's what? It's like what?
Statistical comparison.
Okay.
Using a sample.
How can we use standard error?
Sample data rather than standard deviations of the population.
Well, no, we have a sample standard deviation. That's what we calculate. That's what is 2 times the standard error? What does that approximate? What size confidence? 95% confidence interval. So 2 times the standard error approximates a 95% confidence interval. What can we do with the confidence intervals? Catherine? Does she remember? We can use that for our stats. We can utilize blood donors. Don't include this tomorrow. But we can use confidence intervals as a way to compare our mean to other means, and so forth. So, quick and dirty method is look to see if those error bars overlap. If a confidence interval does not overlap, then there's difference in means. If the confidence intervals overlap and include the means, or include one of the means of the groups, then there's no difference between the groups. If the error bars overlap, but they don't capture any of the means, that's kind of one of the gray areas. Maybe it's different, maybe it's not. Kind of comes down to sample sizes, how much, what our means actually are, and the variances, and so forth. All right, so 2 times the standard error, especially if you plot it on a graph, allows your readers to actually make those types of comparisons. Now, is it typical to plot 2 times the standard error? No. Typically, it's just a standard error, and then it's left up to the reader to look at that. R doesn't have a built-in function. It doesn't have a built-in function as part of its base. All right, there's standard error functions written and included in other packages. It's easier just to write our own script, and this is a script. All right, so general format for the script is we call it something. That's our object. I'm going to call it STERR for standard error. All right, and we're defining it as a function. So we're creating a function that takes a value x. All right, and that x is what we give it. All right, and then that function that's going to run anytime we call standard error is this. So first we take our vector that we give it. It's going to strip out all of the missing data, all of the NAs, and then it calculates the standard deviation and divide by the square root of the length. I am going to fix this one too. Scroll that, let me fix it. Because we don't need all of that is NA nonsense. That's what the NA.rm or NA.omit is doing. So this, missed that one, and let me get Bootstrap too. Go. There we go. That's better. So we strip out all of our missing data, and then what we do is take the standard deviation of our vector, divide it by the square root of our sample size, where length is the sample size. Now, the length function actually tells you how many rows are in that vector, and that includes any NAs that are in that vector. So the length isn't necessarily the proper way. However, we fixed it by removing all the missing data first, and then our sample size is the number of rows in our data set. That's standard error. All right. The other one that we have is a Bootstrap confidence interval. All right, so a 95% confidence interval. We said 2 times standard error approximates a 95% confidence interval. That assumes that the data are normally distributed. All right, normally distributed, and you'll have the same value above, or same range above, same range below. But what if our data are skewed? Does it make sense to have a symmetric confidence interval? No, not at all. All right. Case in point, anytime you're going to see it, if we have this undergrad research symposium, or grad research symposium, you'll see it. You'll have a count where it's like the average is 5, and then they have error bars, and the error bars go all the way to the negative. How do you get a negative count? You can't. That's an example where we're bounded. Standard errors or confidence intervals, symmetric confidence intervals don't work. This is where our bootstrapping comes into play. This bootstrap confidence interval is the same thing as a regular 95% confidence interval, except we use our data to generate. So this confidence interval then is going to reflect the underlying distribution of the data. If we're bounded by a certain number, if we can't go below 0, our bootstrap confidence interval won't ever go below 0. If we're bounded by 100%, our bootstrap confidence interval won't ever go above that 100%. All right? It's actually very, very much preferred to do these bootstrap confidence intervals than to try to make these assumptions that the data are normally distributed. The other nice thing about these confidence intervals is that we can calculate it for any value. So prevalence of an infection is what?
Percentage of the individuals that have the parasite.
All right, so the percentage of individuals that have a parasite. So you have number of individuals that have it, total number of individuals that you look at. It's just a percent. How do we get a standard deviation of that number? You can't. It's just a fixed number. However, we can generate bootstrap confidence interval by repeatedly sampling our data set so we can kind of figure out, well, how wide is our confidence? How much confidence do we have in our actual prevalence values? So how do we do the bootstrap confidence intervals? We've got our object. I call it bs.mean for bootstrap means of our means. We're defining a function where we give it x as our numeric vector. I have it as the sample or the number of iterations at 1,000, and our confidence interval that we're looking for is 0.95 or 95%. Because I should be doing this. All right, so when this runs, the function is going to take your vector, it's going to remove all the missing data from that vector. All right, that helps with our sample sizes. All right, then what we're going to do is create an empty vector, and for our loop, we will sample with replacement. So we have our, let's say, 10 individual fish, and let's say we have 7 fish that are infected. What we're going to do is draw 10 fish out of that set. And we're going to draw one, record it, put it back. Draw one, record it, put it back. Draw one, record it, put it back. So it's possible that we can get all 10 infected individuals. It's possible we get 0 infected individuals from that sample. But we're creating a bootstrap sample, which is resampling with replacement. Once we have that sample, then we calculate the mean of it and we save that mean. All right? And then we repeat this over and over and over again until you get a large number of these means. And then once we have that, we calculate the 95th percentiles. So we are looking at the 95th percentile of that middle part of our distribution, which is for 95%, 2.5% below, 97.5% above. All right. So how do we actually run these? Well, these are scripts, or these are functions. And right now, if I go over here, I don't have anything in my data set. I don't have anything in my environment. So if I just went down into so first I'm gonna load my data set. So this is what we were working on. I'm just gonna go ahead and run the chunk that imports my water and my glycogen data set. It's there. So let's say I want to calculate the standard error of temperature. So water, $10. All right, it's going to tell me, it's going to give me an error that it can't find that strr because it's not a built-in function. We created it. So what we're going to have to do is have another chunk that's going to load our functions. All right, so my function script I have here, I've got both. So you just kind of move them over. And now they're there, but again, they don't appear in the environment yet. So to access them, I have to run this chunk first. And you now see that functions appear in my environment. Now, if I call sterr or bs.mean, R knows exactly what I'm looking for, where to find it. All right, and it's looking for that function, and it needs that numeric vector. So, going back down to here, so standard errors. So remember, load the function, or copy and paste this. Copy and paste the function script, and then run it. All right, so we've run it. Now I can do the sterr water $temp. And when I run that, now R knows where to find it, generates confidence interval, or it generates my standard error, 0.346. All right, so that's standard error. Why don't you do the Bootstrap confidence intervals and see what we get? You should use 10,000 iterations. I do believe I copied and pasted these and had these as like a .r file that you could open up, and it's up to you to kind of get that into your single useful function script. Did you get it? Did it work?
No.
Is it an error message?
There's been nothing completed. Right?
Yep. Is that are those the correct things?
Right.
Yeah, there's
That. Oh, and don't forget your curly braces in R to tell it that that's an R chunk. There we go. Then you can go to the end and close it then or that.
Right.
Then you're not quite done yet. You see how you're indented?
Oh, I didn't know.
So that means when you hit enter, you are indented. You're not done with that function. Yeah, close.
Here?
Yeah, close it down here.
I know.
And then hit enter.
Henry got me
There, you see how you're back. Now let's
really like it. So awesome. It's got
So
sunflower
that's
tops.
Bootstrap.
Oh,
And it says a little privacy, a little trash.
I think I don't know.
I think when I thought it could taste it.
Right.
Oh, no, you already ran it. It's here.
Oh.
Got it.
What do I do with this now?
So now we actually have to run it. So if you have it in,
oh, that's it?
let's move this over. So if you have the function in,
Oh,
so I put this function up as in a separate functions area. Functions, I've got all my functions loaded here. So I've got my standard error, I bootstrap mean, and then when I run this chunk, now my functions appear. Once I have that, now I have to tell R, well, what the bootstrap confidence interval I want. And the one that I want is the temperature data that's in that water data set. So it's gonna that water data set's gonna be the first thing that has to get loaded, and then you can run it. Yep.
Can you get your own?
Yep.
So I want to start at 5.
Yep. Right. Yeah. So sorry on the PDF that was posted. I thought I had caught all of those. Guess this wasn't up there. DS.me and SCR, right? So we have it there. Okay, so let's go to okay, so unexpected slow.
Oh, that's for the
Standard
stuff.
error.
Yeah.
No, we
Did you get it formatted?
You wanna help me?
Which one?
I'm just trying to replace that.
yeah, except I am fucking awesome, so. No, we can use this first. And then so now we can do SDR.
We have the tape, I think that's
So you already have that, so now then that.
That's
After your cheat?
and
Same with this one?
I can just tell by your voice that you're not a
there's
computer
a
science
couple.
major, but
How about you save and open it back up? Save or see. That is weird. All right. I'm just trying to import the water one. I'm getting frustrated. Water. Right here? Yeah. Oh, wow.
Yep.
Oh, yeah. Yeah, you can delete it.
Okay, so it can't be on the same
Yep.
one.
There you go. Yep. Water.
And then time.
Here, right?
Yeah. Did you move it?
Here it is. I don't know why it didn't open.
And then, there you go.
Something
Doesn't do it.
changed. Something changed.
Okay, well, it's here now.
So now it should work, if you close it up. So you've got the water, have your function loaded, right?
Yes. Here.
Okay, so now try like, okay, so now do like your standard error of water $signs. In a chunk.
So,
Yep. Now parentheses. Water. What am I looking at? Yeah, temperature data.
Yeah.
Now you gotta new line.
Hey, Maddie, what'd you get for the standard error?
yeah, work that fine. I didn't work like that.
Standard error,
Using
I
that.
got 0.3455.
Thank you. I got it from the day.
Yeah, copy.
Yeah, coming
Did you, make the?
Dude, I got it all. I got it all. I tried to. I didn't change anything. You know, this one, that's on the orange.
Do you feel like it's something special?
Yeah.
I feel like if it's in that line, maybe.
Something feels, yeah, something feels the wrong time.
Yeah.
The DS means loaded.
No, I don't know, I copied and pasted. I also have like my own little thing that I'm already.
I'm gonna go.
Yeah, I have a bunch of copies.
Yeah, like one more parenthesis.
No, dude, I didn't do anything. Yeah, I just copied and pasted.
I got mine from the Blackboard.
Yeah, that's what I did. I got the two things and tried.
I mean, if you-
Something.
Okay, I'm happy with that.
Who knows?
All right, then.
Yes.
Like going into sitting in a like an hour and
I thought some more GIS.
I don't know if you've ever had those.
Capital H. And rerun that.
First. Hopefully it was fast. Good luck. And like I said,
Yeah, well, no, it should be VS.me. It's gotta be something different.
yeah.
you like to say that?
No space between, function and the function.
Oh, yeah, yesterday I went to,
Yeah. And grill?
Yeah, yeah, we'll grill. I can go through from there, which is kind of weird.
Is it nice in there?
Yeah.
Oh,
Yeah.
VS.me, there, and then no space.
But I was there. Yeah. I was
I
there.
guess it would help.
Yeah.
I didn't.
They gave me.
So that space is okay.
Really?
Now, let's see if there you
I
go.
still have IHOP in there.
Oh, wow.
Yeah, I did it. All right, first
Yeah.
foray into functions and stuff. There's always going to be errors and problems. When we get it running, it becomes second nature. Now, if everyone has it running, you can copy that code into your useful function script. You don't have to go back and try to copy and paste from different things. You've got one, just like I have one. I know this works. I can copy and paste it. It's working, right? All right, so we did that for temp. Bootstrap confidence intervals, really good. Really good to use. If there's any question, if your data are normally distributed, you can just use it. And again, Bootstrap 95% confidence intervals, you don't have to multiply by 2. You look at the intervals, if there's no overlap in the intervals, the means are different. If the intervals capture one or more of the means, they're not different. If they just overlap, it kind of depends on the degree of overlap and it's based on sample size. All right, so we wrote our functions so that we can utilize the aggregate function. All right, so the aggregate function is going to apply a function to a vector for each level of the grouping variable, all found within a known data frame. All right. So the usage of this is aggregate. Y is a function of x, our data frame, and then the function. All right, and anything extra that goes with the function. All right. So what this would do would be to apply whatever function we want to the y variable for each grouping level in the x variable. And all of these are found in the data set. All right? So, practice here. We've made our standard error. Go ahead and calculate the average temperature and the standard error for each of the distances from shore. So the basis with these water, I think I told you, remember we went and took water quality parameters and we measured, when we collected the water, we knew how far from shore we were. So try to get this. And this is where the aggregate function is going to come in very, very useful. We have our y, that's what we're calculating the average of or the standard error of. X is going to be our grouping variable. We've got our data frame that we're working with, the data set, and then the function that we're going to apply, and that is a capital function, right? F-U-N, all caps. And you don't have to, you just give it the function. You don't need parentheses X or anything, just the function.
What is it we're calculating for water? Is it like water, Y, and X?
Average temperature for each of the distances from shore. So did you get the average water temperature? Each of the distances. Yeah. Yeah. Good question. How did you know I used, if you use distance, it didn't work? Right? So, yeah, you look at the data frame and figure out what was a variable name that represented distance? It's feet. So did you get your averages? What's the average temperature for 2 feet from shore? 24.5.
Average.
Mean. No, gotta use the mean function. So here's mine. Aggregate. Temp is a function of feet. Date is water. The fun is mean. So again, verbalizing it, we applied the mean function for our temperature data for each of our categories of feet, distance from shore. All right. And then the aggregate function can be used with any built-in function. All right. So I think I said then standard error, right? So temp is a function of feet. Date is water. Fun is STERR. And it calculates it. Note it. 6. Yeah, and it. What do you think happened? There it is. There's an average. Yep.
I'm getting an error.
Ah, okay.
A squiggly line between temp and feet.
I'm feeling.
Yep. Yeah, this one.
Sorry.
It's because we can't use the equal sign. The equal sign kind of says, hey, save this as memory.
why do we have NA for 6 feet?
There's only one sample.
How'd you figure that out?
I looked at the table.
Looked at the table. Or I could apply the length, my sample size for each, assuming, well, this is, no, this assumes that we don't have any missing data. What about bootstrapping? Okay, gonna work. What? Yes, that means. Uh-oh, what's going on? It worked. Yes, I mean, it worked. Mine's not popping up. I mean, it works in the console. I don't know why it's not outputting it. It is. I've encountered that before. Let me close this and try it again.
Mine's the same way too.
It did.
Wait till the console didn't.
I honestly don't know if this.
Mine's not putting it on mine either.
Right. And it might. You know, I'm gonna have to check it on a different computer. Yeah. It's probably something with the R markdown. It's located, if I pass it here, we can get our confidence intervals, no problem. I don't remember this ever happening in the past. I think this is something that I noticed last year in the fall, and that was when we updated to the newest version of R, which added some nice functionality for the car packages. So that's our aggregate function. Very useful. I mean, especially for this class, we're not really going to be doing a whole lot of one sample tests. A lot of our tests are going to be looking at groups. Do the group means differ? All right. Do the group means differ? How do we generate our summary statistics to make our figures and so forth? And what I did was for the bootstrapping, you can add additional arguments to the functions. So there's many different ways, many different functions that we could use that would fit into this aggregate function. And if they don't have a function, we can actually write our own function so that it does work. So you may find somebody actually wrote the standard error function as part of a function in the code. I just think it's a little bit better, a little bit nicer to make our own function and keep it in memory. All right, graphical displays. So we've got our summary statistics. Now, what kind of graphs? So temperatures, numeric data, measurement area. And really there's only one good way to display these data. Display one continuous data. What is that? It's a histogram. It's the only way, really the only way. You might say we can do a box and whiskers plot. And it's like, no, you really can't. Box and whiskers are for comparing groups. Really, the only way to display continuous data is with a histogram. Now, how useful is it? Depends on what you're studying. All right. Many cases, for what you guys are studying here, it might be best just to report means and standard errors. That's it, and not have a figure. But if you do something like looking at fish, maybe you want to look at size distributions. And this is where a histogram comes into play. So how do we make a histogram? Hist. Simple as that. Right? Hist. For histogram, H-I-S-T. All right. So make a graphical display of that temp data set. Go here, and then we'll show some details.
Yeah, the next string.
All right, so did you make one? All right. So I know it's gonna be in the next one too, because we'll add some overlays to it. But the R function is hist for histogram. All right, and there's some options that we can use for it. All right, so breaks is the first one. We can specify the number of breaks, number of breakpoints, or the number of bins. All right, R does its best to take the number and uses that as a suggestion. All right, we can force it. You know, right now this histogram has 10, 9, has 9 bars. If I wanted 10 bars, I could force it to do 10 bars. But it could be tedious to do it. All right, but if we wanted more, it's easy to change. And you know, we keep increasing the number until we see the change and we make a histogram that we think we like. So for the histogram of water $temp, I can do breaks equals 20. And you can see that it changes it. It might not exactly give me 20 bars or 20 breaks, right? But it gives me more bins, more bars. Right? If I say I have too many, perhaps I want to reduce it down to 5. I can do it. This doesn't give me 5, it actually gives me 4. But, again, R takes the breaks as a suggestion. What about the frequency? So frequency equals false gives us the density. Gives that the proportion. So if I give frequency equals T, it gives me the actual raw counts. So the density, whenever it's F, is more of the proportion of the total that are in that bin, that are in that group. So in this one, we have, I don't know, 10% maybe, 12%, which seems strange to me. But we're going to use this. Normally, if you're just making a histogram, you're going to use the default, which is frequency equals T, and look at the actual just raw counts, frequencies. So I'm going to take out breaks, because I think this one that R makes is pretty decent for us. All right, so we can see that in our most populous group, we probably have 25 maybe, or just under 25 objects. So that's our histogram. It's our one categorical display. How useful is it? Again, depends on what you're doing, what you're looking at. I've used it working on snails. We would use it for working on fish, especially fish or crustaceans that have short reproductive periods, because you can see like cohorts increasing in size and then the new cohort coming in, the histogram and so forth. So maybe you use it, maybe you don't. But that's a histogram. All right. Whatever.
Would you export these plots outside of R? Would you modify like X, Y, Z?
Not that I know.
Outside of R?
Not that I know of. But you can very easily.
Or the labels or anything?
Oh yeah, just do $hist. Go to the help file. You're going to see some stuff. So this gives you all the information, you know, what it takes. And again, there's a ... because it gets passed on to, I think, the plot function, further arguments, and graphical parameters that are passed to plot.histogram. What you're looking at is X limbs and Y limbs. So these are your limits. So like, I don't like how these bars go above the labels, right? I don't like that. So I can specify my Y limits as saying 0 to 30. Whoops, no, Y equals. And you can see I just adjusted our axis. Perhaps I want more room on the x-axis. I can adjust the y limits. All right, and you give it a vector of points, starting point to ending point. And that is defined. R won't mess with that. We gave it its title. It'll go from there to there. Now, what about your labels? Right here, xlab and ylab. So those are much the same way. I don't want it to appear as water $temp. I actually want it to appear as as just temperature. So xlab equals temperature in quotes because it's a string, it's a text. So when I run this now, it appears as temperature. And there's more information. So I also don't like the main. I don't like that histogram of water $temp. I don't like that. So I take it out. Main equals blank. And it's there. All right, so there's a lot of things that you can do with the functions. There's a lot of power to it. If you need to do that, you can come talk to me. I can help you out. We're not going to spend a whole lot of time because we could probably have an entire class just on graphics and all, where you learn how to do this. How you make your plot, where you've got like 2 plots up top and then 1 big plot underneath it, and it makes a nice plate. For you guys, I think you just make the 1 graph and then copy and paste it into your Word document and move it around after you release it. No one will know the difference. Right? Except me. Now that I mentioned it, I'm going to ask. How did you make these graphs?
You add color in art? You want to add color to those bars?
Oh yeah, you can change the shading. I believe you can do patterns. So that is over here.
I want to get you on top.
Color right here, light gray. Cover. I think you can see it. Yeah, you can adjust the color.
Like 5 different.
The angle. So the density and the angle, I believe. So I think the angle is related to hatching, cross hatching. But don't quote me. What was the function? Plot.histogram. So the main is like equals everything. Yeah, angle and density, that's the shading of the bars. So if you didn't want to color, if you wanted hatching instead, you can do that. I have messed around with that. But again, it's just trial and error, making it until I think it looks okay. All right, so these are all summary statistics. We're presenting them. How do we round it? How do we round our data? How do we round our sums? How do we round our mean, our standard errors, confidence intervals, and so forth? All right, so here's what we can't do. We can't round to any more digits that we're measuring. All right, so if we measured length in millimeters, we shouldn't be rounding it to hundredths of a millimeter. We didn't go that far. Right? We also can't round to more digits than the precision of the instrument. So if I go up and measure grams on my balance, I can go up to thousandths of a gram on there. Right? Actually, thousandths of a kilogram on it. So I wouldn't go to like millions of a kilogram. Right? The machine doesn't work like that. All right? So anytime we record the data, we take a measurement and you record it based on the precision of the instrument that we have on hand. All right. Now, what about the means? Well, the means are always going to go to 1 more digit than what was measured. So that accounts for those possibilities where you get that half. You can actually see the half between those 2 measures. All right. The standard error goes to 1 more digit than the mean. So if your measurement was a whole number, all right, your mean is going to have 1 decimal place. Your standard error is going to have 2 decimal places. All right, now there's a finer way to check. Does anyone remember how we did that? How we figured out where to round our means and standard errors?
Divided by.
And the inverse then. Yeah, standard error divided by 3. So whatever we had, just as a quick example, let's say our standard error, I don't know, give me a number.
12.
What's that?
12.
So standard error is 0.12. That's what we calculated. Exactly, that's what R gives us. What we do is take that 0.12 and divide it by 3. All right? That is our first non-digit number. Non-zero number. It's our first non-zero number. So we round our mean to that point. So, I don't know. And then our standard error gets rounded to one more digit. All right? That's how they teach in the textbook. It's been kind of my feeling and just kind of my general observation that this method basically gets us to this. Pretty darn close. All right? So means and standard errors go basically based on your precision of the measurement. What about your test statistics? So we're going to be reporting chi-square values, f values, t values. Typically, we go to 2 decimal places. There are very few exceptions. One of them is with the Shapiro-Wilks test, where our test statistics is 3 digits. So if you get a t value, a t statistic of 3.8494123, we don't report that entire number. We only go to 2 decimal places. Same thing with an f statistic. All right, what about p-values? Well, p-values, where we round depends on the value of that p-value itself. All right, so for very small p-values, anything less than 0.0001, our convention is just to report it as p less than 0.0001. All right, that's convention. Just report it as that. All right, we don't need to see 2 times e to the negative 16. We don't need that. Just p is less than 0.00001. All right, if our p-value is between that 0.0001 and 0.001, then we use 3 or 4 decimal places depending on where we're at. So that range, until we get up to that 0.001, we're going to use 4 digits, 4 decimals, which basically gives us 0001, all the way up to 0009. Those are going to be our options that we round to. And then when you get up to here, then it's going to be to the 0.01, which I have up there. So now it's going to be 0.0012 all the way up to 9. All right, so we don't need to see 0.0015. We don't need to see that. 0.001 is sufficient. All right, and that's kind of where I break these are. Once you get up to 0.01, all right, anytime you have that p-value at 0.01 or greater, then it's been conventioned around to 2 decimal places. And again, there's going to be some exceptions if our p-value is really close to 0.05. So if you get like 0.046, right? You can say it's less than 0.05, and it's true. But if you round it, that number, it rounds up to 0.05, which technically, again, our p-value is less than or equal to 0.05. That works. But what happens if you get 0.051? That's slightly higher, right? If you rounded it, it's to 0.05. At that point, I would say 0.051, just to emphasize we are just slightly above that 0.05 threshold. Now, statistically speaking, we would say that, yeah, there's no difference. biologically speaking, that's another matter. It's so close that maybe there's an effect. We're getting close. Maybe a few more samples, you have a smaller p-value. All right? And anytime you do these calculations, don't round until the very end. Hopefully you do that. You do that. All right, so here's our practice problems for water.csv. All right, algae, feet, and DO. This is in our water.csv data set. So for algae, make a histogram, calculate your mean, variance, range, and standard errors. For feet, make your histogram and calculate these values. And then for DO, and this is a lowercase d and then a 0. If it doesn't work, then use a capital O, but I'm actually it is a capital O. It is a capital O. What am I saying? It is a capital O. It's dissolved oxygen. Make a histogram and then calculate these values. All right. Use the function and it doesn't work because it says it can't find the object. You don't remember what that function was? Feel free to Google it. Just type in the name and then in R, and it'll probably be like the top hit. This is how you do this statistic in R.
Oh, no. Alright, where are we hung up on? What am I gonna have for dinner?
Okay, so hold on. This
Leftover
dollar
tacos.
sign.
Oh, good. That's what I cook on my own. To make sure I cook the tastiest food. It's cheaper if you're kind of talking. Fine.
Are they tacos in
Yeah, they're tacos.
I don't know if you can call them that.
Actually, it's crazy.
Sometimes
Put a bunch of dough down. Sauce on it. And then you throw the meat out and just roll it out.
Are you saying that the pizza is just the Italian taco?
No, it's in the fire.
I will disagree. I would call it calzone.
That's the Italian burrito.
Maybe more like a chimichanga.
Oh, the Italian chimichanga is the calzone.
That's my vote, that's what I say.
Definitely an empanada.
Empanada, maybe?
Oh, empanada is
That's what they call it.
Yeah, you're right, it's the same thing.
That was my idea, by the way.
America is
Oh,
hot
good
dog.
call, Alex.
Hell yeah. Those are Americans apple pies.
Hot pockets and those little McDonald's apple pies.
Yeah, those are good, but they almost kill me every single time.
Well, because they're so hot.
Yeah, because I feel like I can eat it way sooner than I can.
They hurt so bad.
Yeah.
They just scald your mouth. Instantly.
No.
Brittany, you hook us up with some crawfish?
Maybe.
You load your car down when you come back.
I mean, that's a 9-hour drive. If you guys are willing to
That's
pay
gonna be
money
so-
to bring you crawfish and drive it 9 hours over here, I'll do it for you.
We'll meet you halfway.
Huh?
Yeah.
We'll meet you halfway down there.
Yeah, we don't need to go 9 hours though. You just like stop like a fast drop or something.
Yeah, you can say hi to my mom. Yeah, they probably.
Yeah. It's probably not as good as Louisiana crawfish.
No, probably definitely not as big.
They're small.
Everything is
They're real small in Colorado.
You're
talking about
you
Louisiana
guys in the
crawfish.
middle of the night. And just like opening up her
From
trunk.
She's got like a bed sheet down or something, and it's like water in there, like a tarp.
Trench
Live crop chest.
Here we go.
Alright, so seems to work.
What are you doing with on beach?
This. And I prefer.
We don't have time.
Alright, so yeah, I got it going. It was just kind of making sure all the exercises work, giving you practice doing these, making the chunks, getting it to work. So I've got my histograms, summary stats. Here's this histogram I did on that one. So summary stats, histogram of the oxygen. Now, your bootstrap means, this is what I got. Did you get the same numbers?
For which one? There's slightly.
These?
It's all
Oh yeah, no, mine is different.
Very close.
Why are they different? I mean, that's the same, right? 8.4119? Why are these different? No? No?
Randomly sampling your data.
It's random sample of our data. So, depends on it. I mean, if we only had 10 samples and we did 10,000 iterations, yeah, in that 10,000 iterations, we're going to have the same samples. Just they'll occur at a slightly different frequency. When you have a large data set and you run 10,000 samples, you're going to get some variation. And that's just the random nature. How do we fix it so that we get the exact same number?
Set the seed.
Right? Set the seed function. If we wanted to do that. But for the most part, I wouldn't. If I was just doing regular analysis, I just let R pick its own seed. All right? So if you didn't finish this, go ahead and finish it. Make sure all of this works, that you can do it. If you stumble, please ask me at the start of class. Let's get this working. Make sure we kind of get. We don't want to fall behind. We don't want to fall behind. All right. So where are we going with this? This was summary statistics. Next up is actual basic stats. So we are going to start with one sample stats, kind of review t-tests, z-tests, sign tests, how to do that in R. You might, you didn't take this class from me. It's good to kind of have some of that information again, just kind of review it, and it's a good review to kind of get into the thought process of what are the null hypotheses, what are the alternate hypotheses of all these tests. What do I have to present in the write-up? What do I have to include? All right. I don't know how long that'll go. There's practice problems and so forth associated with that. And then after that, we have our ANOVA introduction. That'll be somewhat extensive. Because it's not just ANOVA, right? What else do we have to do? What else do we have to do with ANOVA? We got to check our assumptions first, right? What happens if we violate assumptions? Then we got different tests, right? That's all part of ANOVA. And then what happens if ANOVA says that group means are different? Yeah, then we got to do post hoc tests. So this isn't just here's how to do ANOVA. This is the batch. This is how we do it. These are the assumptions. These are how we check the assumptions. This is what happens along the way, depending on our p-values and so forth. All right. So, we're done. On Wednesday, we will finish a little early. I do talk to tri-betas. Do you see the sign out there? Present. I was probably just as shocked as you were to see my platform.